Hello students, myself Dr. M. Gunasekaran, Associate Professor from the Department of Orthodontics and Dentofacial Orthopaedics, Vinayaka Mission Sankaracharya Dental College, Salem. In today's session, we are going to discuss about soldering and welding in orthodontics. The following are the contents we are going to discuss in the topic today. Let us start from introduction. What is soldering, welding and brazing? These are all the techniques used to join two or more metal pieces together using heat. The main difference between soldering and welding is the fusion of metals. In dentistry, the terms soldering and brazing are often used interchangeably, but technically speaking, all the dental joining processes are considered as brazing. While brazing uses higher temperatures above 450 degrees centigrade and stronger filler metals than soldering. So, brazing is the right word than soldering. The word soldering is most often used in electronics and in automobile industry. Coming to the next slide, we are going to discuss about brazing. What is brazing? Here, as said above, the temperature is greater than 450 degrees centigrade and stronger filler metals are used. Using a filler metal that has a lower melting point than the base metal or the parent metal to join them helps to form a joint by capillary action. This is done at a higher temperature than the soldering but lower than that of the welding. So, brazing is the intermediate between soldering and welding regarding the temperature. Joints formed from brazing are stronger than the soldered joints but not generally as strong as the welded joints. Next is the soldering. As said, soldering uses lower temperature below 450 degrees centigrade for melting the filler solder metals. Uses of soldering is mostly in electronics, and it is the lowest temperature among all these three processes. Among all three, that is brazing, soldering and welding, soldering uses the lowest temperature for joining the metal parts. It produces the weakest joint also, but it can be used when the strength is not the requirement. Commonly it is used in electronics, plumbing and in other applications where strength is not so important, but ease of use is very possible. Coming to welding, welding involves melting the base metals at the joint, fusing them together. So, it uses high temperature and produces the strongest joints with the joint strength potentially exceeding base metal strength, that is the parent metal. It has wide range of application including construction, automobiles and aerospace. Now we will see what are the ideal requirements for dental solder. Dental solder is used in the oral environment, so it should be biocompatible, that is, it should not cause any adverse tissue reactions. Since it is used in the oral environment, it should withstand tarnish and corrosion resistant. It should have wetting property, that is the ability to wet the parent metal. Next is the flow. It should have sufficient fluidity at low temperatures. Matching properties should match with that of the parent metal, that is the melting temperature, color and mechanical properties should match with that of the parent metal. The strength and hardness should also be comparable to that of the parent metal. Materials required for soldering are the substrate metal, that is the parent metal, and next is the solder, that is the filler metal or the third metal that is going to join the broken parts. Next is soldering flux, soldering anti-flux and soldering investment. All these materials are required for a proper soldering. Coming to dental solder, they are alloys that are used as intermediary or filler metal to join two or more metallic parts. The fusion temperature of the solder should be lower than that of the parts to be joined ideally 50 to 100 degree less than the parts being joined. The dental solder is applied in spool form as well as in straight length. Coming to composition of dental solders, most of the dental solders are designed for specific dental applications, and the composition also depends upon the metal being soldered. For gold alloys, the gold content is 45 to 85 percentage. Next is the silver with the 10 to 35 percentage. The role of silver is improves the strength and gives color to the metal. Next is the copper with a content of 5 to 15%. It provides strength and lowers the melting point. Next is the zinc, 1 to 3%. It acts as an deoxidizer. Next is the lowest content is the tin, that is 1 to 2%, helps in lowering the melting point, and it also increases the flow of the solder. Coming to non-precious alloys, that is the base metal alloys, the nickel and chromium are acting as the base metal. Copper or silver is added to adjust the melting point and improve the flow. Silicon or boron can be used for oxidation resistance and strength. Coming to types of solder, we have two major groups, soft solder and hard solders. Soft solders generally have lower melting range of about 260 degrees centigrade. They lack corrosion resistance and so not suitable for dental use. Examples include lead tin alloys. They are called as plumber's solder. Coming to the hard solders, they have higher melting temperature, therefore they have a greater strength and hardness. They are melted with the help of the gas blow torches, sometimes using an electric furnace. Hard solders are most commonly used in dentistry and in orthodontics. They are used for industrial purposes in the jewelry making. Examples include gold solders and silver solders. Next is the fluxes. Coming to flux, the word itself is a Latin word meaning flow. The flux is the substance that is applied before soldering process. The main role of flux includes increased wetting, increased flow of the solder, and prevents the oxidation of the metal during soldering. This picture shows the silver solder flux. Coming to functions of flux, the flux provides the following function. First is the prevention of oxidation. During heating, the metals tend to form oxides that hinder the flow of solder and adhesion. So flux removes the oxide layer. So it prevents the oxidation. Next role is improves the wetting. By reducing the surface tension and allowing the solder to flow smoothly and bond properly, the greater strength of the joint is obtained. Not only flux improves the wetting, it also cleans the surfaces from impurities and dirts that may interfere with the soldering. It also promotes solder flow by capillary action to ensure the complete joint filling. Next is the types of fluxes. We have three types of fluxes. Type 1 is denoting the surface protection, type 2 is the reducing agent, type 3 is the solvent. As the name suggests, type 1 is the surface protection fluxes. They cover the metal surface and prevent access to oxygen so that no oxide layer can form. Coming to reducing agent, that is the type 2 fluxes, they are opposite to type 1 fluxes. They reduce any oxide present and exposes the clean metal for soldering. Type 3 fluxes are solvent fluxes. They can dissolve any oxide layer present over the soldering material and carry it away. Most of the fluxes are combination of the two or above. Coming to fluxes for noble and high noble alloys, boric and borate compounds are used. Boric acid 35%, borax 55%, silica content is 10%. These three are used for noble metal alloys. They act as type 1 protective fluxes as well as reducing fluxes, that is type 2. Here the boric acid lowers the fusion temperature of the alloy. For the high base metal alloys, we use fluoride fluxes. The oxide layer formed on the base metal alloys are more stable and difficult to reduce. So, fluoride fluxes or type 3 fluxes dissolve the passivating film formed by the chromium, nickel and cobalt oxides. Coming to composition, the fluoride fluxes contain potassium or sodium fluoride 50 to 60% and 25 to 35% boric acid. Borax in the ratio of 6 to 8% and potassium and sodium carbonate 6 to 10%. Coming to antiflux, antifluxes confine the flow of molten solder over the metal being joined. That is, the role of antiflux is to confine to the particular area where the metal should melt and flow easily. It prevents the extra movement of the molten metal. So, commonly used antifluxes are lead pencil, graphite, which is applied as a thin film to block the solder flow, iron rouge, commonly called as ferric oxide. It is mixed with alcohol for easy application. Grease based substances can also be used to protect the adjacent areas. We have three types of soldering: investment soldering, freehand soldering, oven or furnace soldering. In investment soldering, we use large metallic parts and we use when the joint is needing high precision. That is, when precision is important, we have to stabilize with the help of the investment material to solder the joint. The procedure is, investment material is mixed, the metallic parts are mounted over the investment material allowed to harden, leaving a gap between the metal parts. Flux is applied, then heat and solder are applied and the joint is formed. Next method is the freehand soldering. In freehand soldering, the material is held in contact by the hand manually while the heat and solder are applied. The process involves without the use of investment. Next is the oven or furnace soldering. Here, controlled heating environment is available. The electric current passing through the electric furnace heats the metal and forms the soldering joint. Next, we will go to the recent advances in soldering technique. Infrared soldering. In infrared soldering, 1000 watts tungsten filament quartz iodine bulb is used. It is a non-contact heating process. It is mounted at the primary focal point portion of the gold plated elliptical reflector that is acting as the heat source. It reduces the risk of damage to sensitive components or substrates. So, infrared soldering provides non-contact heating. Next is the hydro soldering. In hydro soldering, we have two units, one that produces the hydrogen gas, the other one is the flame controlling unit. It is used to produce reducing flame of hydrogen gas, which can effectively solder stainless steel without oxidizing the components. It produces precision fine flame for soldering. Coming to the steps in soldering, the following should be followed one by one to get a perfect soldering. First, we have to clean the surfaces to be joined, then we have to assemble the metal parts to be joined, then we have to select the appropriate solder and flux, then we have to make a proper joint, then apply the flux and antifluxes, then heating and introduction of the solder is the next step. Finally, it is quenched in water, then soldering is completed. We will see one by one now. Cleansing the surfaces to be joined. This is performed to remove the dirt and contaminants so that weak joint is not produced. We have to clean the surfaces so that any impurities that hinder the joint should be removed. Next is the assembling the parts to be joined. The parts are stabilized with help of dental plaster or stone, leaving a gap of at least 0.5 millimeter between the parts to be soldered. Sometimes we can use sticky wax also. Whenever precision is needed, we have to go for investment method of soldering. Next is the assembling the parts to be joined. This picture shows the correct gap between the metals to be joined. The larger gap leaves a larger gap, therefore this is tend to for more prone for fracture. Overlapping without gap is also not satisfactory. So proper correct gap should be needed for the solder flow. Next is the selection of this proper solder and flux. Based upon the metallic parts to be soldered, we have to select the appropriate solder and flux. They should have the fusion temperature less than that of the metallic parts to be soldered. Coming to making a proper joint, the proper joint is formed by good soldering. The point contact is of inadequate strength. Rather than making a point contact, we can wrap the wire around the another wire that to be joined, which will give good contact by wrapping. This joint will have more strength compared to the point contact. The another method is we can fold the one part of the metal and increase the length to be joined. Longer areas of joint are created, therefore the strength increased. Sometimes we can wound a thin wire over the thicker wire for better soldering like this. Application of flux and antifluxes. These fluxes are applied to the assembled units as well as to the area of portion that is going to be filled by the metal. So fluxes help to remove the impurities and dissolve the oxides, whereas antifluxes will confine the flow of fluxes. Next step is introduction of heat and solder. Heat is applied to the assembled parts by using soldering torch. The dental solder is introduced once the flux begins to fuse. The flame is maintained till the filler material completely flow into the joint. Till then the flame has to be maintained. Then next step is quenching. Rapid quenching in water limits the spread of heat and the assembly is cooled down. We will see the heat source for soldering purposes now. The heat sources often used are gas torch. The flame must have enough heat not only to melt the filler metal but also to compensate for the heat loss to the surroundings. The flame should have high temperature and high heat content. Low heat content will be inappropriate to melt and it will take longer time for soldering as well as more danger of oxidation. Heat content is measured in BTU per cubic foot of gas. This slide shows the picture of gas torches and the electric furnace. Most commonly used is gas air or gas oxygen torch. Electric furnace provides controlled heating mechanism. The gas torch should be properly held in the free hand so that the thumb rests on the knob that is going to be pressed to initiate the flame. Coming to the flame of the gas torch, it has 4 zones. Cold mixing zone, that is the unburned gas. Next is the partial combustion zone, that is oxidizing zone. Next layer is the reducing zone. The innermost layer is the oxidizing zone, that is containing the burned gas. Coming to torch flame, the torch flame should be held properly. Improperly holding the torch leads to the oxidation of the substrate or the filler metal, results in poor joint. Also, introduction of the unburned gas portion of the flame leads to carbon deposition in the substrate and filler metal. To prevent oxidation, flame should not be removed once it is applied until the soldering process is completed. The flame provides protection from oxidation, especially at the soldering temperature. Coming to the zones of the flame in detail, which portion of the flame should be applied. We have to apply the tip of the reducing zone because it has more efficient heat content. So the tip of the reducing zone is the ideal zone for soldering the assembly. So it is also having more efficient burning process and higher generation of heat. So the best zone is the tip of the reducing zone. This zone area is the correct area that to be pointed over the soldering material. Coming to gas sources, various gases are used: hydrogen, natural gas, acetylene, propane and butane. But hydrogen has the lowest heat content of 275 BTU and it is not indicated for soldering large bridges. Coming to natural gas, it has 4 times that of the heat content of the hydrogen, but it is non-uniform in composition and so frequently contains water vapor. So natural gas is not so ideal for soldering purpose. Coming to acetylene gas, it has highest flame temperature, higher heat content than that of the H2 and natural gas. But the problem is the flame temperature varies more than 100 degrees centigrade from in different parts of the flame. Positioning the torch also is very critical. The proper part of the flame should be used. Chemically it is also unstable, decomposes to carbon and hydrogen. Carbon may be incorporated into nickel and palladium alloys. Hydrogen may be absorbed by the palladium alloys. Next is the propane. Propane is of best choice with the highest heat content of 2385 degrees centigrade. Coming to butane, which is more readily available, it is also similar to propane in uniform in quality and also water free. Most of the commercially available gas torches uses butane. Coming to the clinical applications, the soldering process used to join the wire to the wire, wire to the bands, for joining the attachments to the molar bands and to join various components in fixed partial prosthesis, repair of the crown and bridges and for soldering the clasps in removable prosthodontics. Coming to application in orthodontics, various appliances need soldering. Example, quad-helix, lingual arch, Hyrax maxillary expander, space maintainer appliances like band and loop, Gerber space maintainer, transpalatal arches, fixed tongue grip, W arch appliances. These are the pictures of appliances. The arrow points to the soldered joint. The molar band is adapted. The wire is soldered to the molar band. This is the lingual arch appliance. Here Hyrax expander is soldered to the bands attached to the molar and premolars. Next is the band and loop space maintainer. The arrow points to the soldered joint. This is another space regainer, Gerber space regainer. One premolar and molar bands are attached and soldered. Here transpalatal arch needs soldering. Here also fixed tongue grip. In this fixed tongue grip, molar bands are adapted. Tongue grip is soldered to the molar bands. This is a Nance appliance which contains the 2 molar bands that are soldered. Even quad-helix appliance needs soldering at the molar bands. Next we will be seeing the welding process. Welding process is similar to soldering, but we do not use the filler material. Here the fusion of the 2 or more metal parts by application of heat and pressure, but without the filler material. So it produces a localized union across an interface between the parts to be joined. What are the materials used in welding? Titanium, stainless steel, alloys made up of gold, alloys of cobalt chromium, alloys of nickel and chromium. Mostly titanium is used in dentistry. Next is stainless steel. The gold is very expensive and not used nowadays. Coming to methods of soldering, based on the melting of the parts, we have 2 methods. One is the fusion welding, next is the pressure welding. In fusion welding, the parts are melted and joined, but pressure is not applied. Example, arc welding, gas welding and laser welding. In pressure welding, the parts are heated and pressed but not melted. We have 2 types, resistance spot welding, resistance seam welding. Coming to welding classification based on the application of heat and pressure, we have 3 categories: cold welding, hot welding and spot welding. What is cold welding? Cold welding is otherwise called contact welding or solid state welding process. Here the material is plastically deformed at the room temperature accompanied by strain hardening. It is done by hammering under pressure without heat. Example, gold foil filling. Next is the hot welding. Hot welding uses sufficient heat intensity to melt the metals being joined. Usually oxyacetylene flame is used. Sometimes high amperage electricity can also be used for hot welding. Next is a spot welding. It is a type of resistance welding to produce a localized bond created by applying heat and pressure to melt the metal at a particular location. Uses in orthodontics includes welding bands, joining the attachments to bands, joining fine springs to heavy wire in removable appliances. Example, apron spring. In principles of soldering, we use two principles, that is heat and pressure. This is the assembly. Two electrodes are present that going to apply the pressure over the area to be welded. The main supply is connected to the two ends of the electrodes. The force is applied through the spring mechanism. We will see in detail in the upcoming slides. This is a spot welder we are going to see. It has following parts: electric transformer inside the welder, copper electrodes are of different sizes mounted over the two members, upper and lower. Spring mechanism helps to make contact between the two electrodes here. Timer switch is available to adjust the timing of welding. This is a circuit diagram of the spot welder, orthodontic spot welder. This is a P stands for the primary winding of the transformer, C is the core of the transformer, T is the timing switch, S is the secondary coil, secondary winding of the transformer, TA tappings on the primary winding. This is the resistance variable resistance. These are flexible springs which conduct the current to the upper electrodes and exert pressure over the workpieces. L stands for the lower electrode holder and E stands for the electrodes. This is the circuit diagram. The main supply is here, timer switch is here, electrodes are here, primary coil, secondary coil. We will see in detail. Electric transformer is a step down transformer, produces the low voltage high amperage current. The resistance offered by the stainless steel is so great that the high amperage current generates very high temperature at the electrodes. The metal under the electrodes become plastic enough and the copper electrodes simultaneously apply pressure, so the metals are squeezed and form the joint, weld joint. Next is the copper electrodes. The copper electrodes are mounted like this. We have different shapes of electrodes. They transmit the current. They have low resistance compared to that of the stainless steel. They also conduct the heat produced during soldering away from the electrodes. They also hold and apply pressure over the metal being joined. They have different diameters. Different diameters are indicated for different purposes. This is a smaller diameter, can be used for spot welding. The larger diameter can be used to create a larger weld. This is a spring pressure mechanism. This works to hold the pieces to keeping in contact until the timer switch is turned on. Next is the timer switch. It controls the duration of current flow. The passage of the current at the weld spot is very short duration, just not more than 1/10 of the second. If it is allowed to pass more duration of current, weld decay will happen. That is due to the precipitation of carbides from the metals. So to prevent the weld decay, shorter time is applied. The working voltage is variable by means of tapping the timer switch on the primary circuit of the transformer. This is a primary circuit for the welding. This is a spring pressure mechanism. Here is a timer switch. Next is the procedure of spot welding. We will see how to weld using the electrodes. So first we select the proper electrodes for welding. Based on the thickness and the shape of the material to be welded, the electrodes are selected. Thin materials is used for broad electrodes, thick material is used for narrow electrodes. Before making the weld, the electrodes should be cleaned to remove any carbide and dirt. Next step is the proper placement of the metal bands to be joined between the electrodes. You can place it using the hand or using some pliers to hold the bands between the electrodes like this, as shown in this picture. Here we manually keep the bands using the hand. Here we use pliers or Matthew holder to apply the bands. Next is the timer switch is turned on. When the timer switch is turned on, current flows for a few seconds to obtain the good joint. We will see the factors influencing the welding of a stainless steel. So 3 factors influence the welding process: current flow through the circuit, time during which the current is allowed to flow, the mechanical pressure applied at the weld head. These all determine the proper joint. Next we will be seeing the recent advances in welding. Coming to laser welding, it provides monochromatic coherent collimated intense light beam. Most widely used is ND arc laser. It provides precise and sensitive metal can be welded. It gives more precision and accurate welding is possible. Next is the benefits of laser welding. We can able to weld even small components. We can make high precision welding. It contains narrow heat affected zones, no oxide formation because of the inert gas atmosphere. It also reduces the galvanic corrosion. Next is the electric welding. Coming to electric arc welding, it is a fusion welding process. It joins the metals by heat generated from the electric arc to melt the metal at the contact point, thereby creating a strong fused joint upon cooling. The electric arc welding is less frequently employed in dentistry. The benefits include ability to link range of metals and high strength of welded joints. It is used for connecting brick bridges like implant supported restorations and dental prosthesis. Let us see the working principle of an electric arc welding. When the electric current is passed through an air gap from one electric conductor to another, an electric arc is created, which produces very intense and concentrated heat. Here we have the 2 electrodes connected to the terminals. Workpiece is placed here and there is a small gap. When the electricity is passed, this air gap is the area where the electric arc is produced. When the current passes through this air gap, electric arc is produced and generates very high heat, and intensity of the heat is also great. Electric arc welding can use either AC or DC supply. One electrode is connected to the welder, the other is connected to the workpiece. As mentioned earlier, the circuit is completed through the air gap between the electrode and the workpiece, creating a electric arc between the electrode and the workpiece is the welding process. The temperature obtained is very high, around 3500 degrees centigrade to 400 degrees centigrade. The metal in contact with the arc becomes molten and able to weld a melt. The electrode is moved slowly in the desired direction to complete the weld. Metal inert gas welding. In case of metal inert gas welding, continuous solid wire electrode is heated and fed into the weld pool from a welding gun. Inert gas such as argon, helium is used as a shielding gas to protect the weld pool from atmospheric contamination. Next is the tungsten inert gas welding. The electric arc is stuck between a non-consumable tungsten electrode and the workpiece. Tungsten inert gas welding is also known as gas tungsten arc welding. It uses a non-consumable electrode, so we need some filler material for welding. So we add some filler material in case of tungsten inert gas welding, which is not needed in the previous, that there is the metal inert gas welding. Let us see the difference between MIG welding and TIG welding, that is the metal inert gas welding and tungsten inert gas welding. Here we use consumable electrode. In tungsten gas we use non-consumable electrode. The electrode itself acts as the filler, but here we need additional filler, that is a material rod to act as a filler. In MIG welding, the composition is similar to that of the base metal. Here the tungsten electrode is used. So the composition is different. In MIG welding, gas shielded metal arc welding, the gas shielding protects the weld pool from the atmospheric contamination, whereas here the gas shield is a tungsten arc welding. Compared with the tungsten arc welding, metal inert gas welding is much faster, whereas tungsten gas inert welding is slower. The other differences are spatters are usually produced in MIG welding, whereas it is free from spatters in TIG welding. In MIG welding, it is free from tungsten inclusion defects. In tungsten inert gas welding, the broken part of the tungsten electrode gets embedded and therefore it is contaminated. The quality of the joint also not very good in MIG welding, but in tungsten inert gas welding we have a good quality and appearance. Coming to application in orthodontics, the welding is usually done for the metal strips during banding procedure, for fixing attachments such as the brackets, cleat buttons and molar tubes to the bands. These are the places where we apply welding. From this what we gather, the message is proper soldering material determine the good soldered joint. If the joint is to be good, we need good soldering materials. Good joint increases the success rate of orthodontic appliances. Similarly, the good welding prevents the breakage of orthodontic appliances. So avoiding failures in soldering and welding improves the quality of orthodontic treatment. Thank you.